Trane chiller, economizer. Please explain. Absolutely. So the whole purpose of an economizer, let's start there really quick and I'll get into the whiteboard and we can kind of draw some of the refrigeration cycle around that. The whole purpose is to improve the overall efficiency of the chiller. And we can do that by making better use of our refrigerant to not only reduce some of the load on the compressor, but also we can improve our effectiveness of the refrigerant by reducing what we call enthalpy. Enthalpy is the actual heat content of our refrigerant. Without getting crazy into enthalpy as a term, the point is it's just showing us the amount of heat that something contains. The economizer allows us to lower the enthalpy, which allows the refrigerant to be more effective. But it also allows us to reduce some load on the compressor. So let's get into some actual diagrams. This here is part of our enthalpy chart. Okay, we'll come back to this. All right, I'm not going to spend a ton of time on it. We don't need to. This is just going to kind of give you an idea. Now, being the fact that you said it was a Trane chiller with an economizer, I'm going to assume you're referring to a Trane CV series. We're going to go with, say, a CVH. This will be true for an E or an F. This particular schematic is true for an F. Now, I'm just talking about the model of the chiller. So when you look at the model number, the first few letters, for Trane specifically, is going to be the first 4 that you're going to look at. If you have a CV or CD series with an economizer, this is going to be something that is kind of a basic concept we're going to follow. Now, from a refrigerant perspective, let's draw that. So let's continue with the CVHF perspective. The CVHF has 2 impellers instead of 3. We're gonna stick with the CVHFs for a simpler. So we have an impeller, and then we have our next impeller. We're going to put this inside the compressor. Okay, here's our nose cone. Come down into our evaporator. And then we're going to have our actual economizer. We're going to call this the econ. And then coming out of our discharge, I'm just going to draw this as a pipe up here. Very crude schematic, but you'll get the general idea. This is our condenser. And then our drop leg comes out into our economizer. Then we have another leg coming out into our evaporator. Guide vanes here. All right, so this particular one is just going to have a single pipe coming up right here. So everything's going to flow. Let me get some color involved here so you kind of see the process. So we're going to have low pressure. Purple is going to be our medium pressure. We've actually got 2 medium pressures here. Let's see. Well, this one doesn't have an internal. So what? Yeah, this will work. This will work. Going to be purple here. Right here is going to be low. And then we're going to do red, high pressure, high pressure. And then here in the compressor, we have medium pressure coming in. So low pressure coming in, medium pressure. This is the basic refrigeration cycle for our Trane CVH series or CDH. Okay, now this specifically of 2 impellers, so this is going to be our F series in this lineup. What's happening here? The evaporator is going to function the same. This is a flooded style of evaporator. Refrigerant's going to sit over the tubes. It's going to boil off. Vapor, superheated vapor comes back into the first stage impeller. This is going to be first and then second. So it's a multi-stage design compressor on these. This is very important. Okay, this is not specific to just Trane. Trane is not the only company that does this. But it's important to understand that to make this work correctly, we need a multi-stage compressor. If it's just one impeller, single stage, this same concept wouldn't work exactly the same. So we have superheated vapor coming off. Now this vapor is going to be 0.5 degree Fahrenheit, 1 degree Fahrenheit, superheated coming into our compressor. It sounds really low, but this is normal for centrifugals. We've got a set of guide vanes right here. These guide vanes are controlling the refrigerant flow coming into the front of the impeller. If you haven't seen an impeller before, yes, I have one on my wall right here. So uh, this is a very small impeller. Okay, this is not what you'd find in a Trane, but this comes out of a turbo core. But it's the same basic design concept that you would find in the Trane. The impeller it's just going to be bigger, larger scale, but for the most part, the same basic design on the impeller itself. So there's a physical representation of what an impeller actually looks like. You can kind of picture that inside of here. So we've got a set of vanes that are basically just paddles that are controlling the refrigerant coming in. This impeller takes a refrigerant to a medium pressure. So we go from low pressure to medium pressure. That medium pressure then gets fed into the second impeller, which goes from medium to high pressure. So it's a two-stage cycle on this. If the three impeller designs for these, where there's three of them, we just go from a medium or a low pressure to medium low to medium high, and then medium high to high pressure. So that's your staging sequence for a three-stage versus two-stage machine. So out of here we come high pressure refrigerant. Discharge gas comes into the condenser. Condenser condenses the discharge gas accordingly. So these are both water-cooled heat exchangers, condenser and evaporator. These particular condensers generate a very minimal amount of subcooling. Basically, it's just enough subcooling to essentially ensure that we have a full column of liquid coming into our drop leg. So the drop leg, or the liquid line, is the line leaving the bottom of the condenser. When we come down out of this line, so we're still a high pressure liquid refrigerant, so high pressure superheated discharge gas, high pressure slightly subcooled liquid refrigerant. We come into a flash plate. It's just a fixed orifice, all right? Just like with a little split system heat pump with a little orifice in there, something like that. This is just that on a much larger scale. It's actually a perforated plate, so it's just one steel plate with a bunch of tiny little measured, engineered pinholes in it that creates a pressure drop for us. But once we go through this first stage of pressure drop, we're not actually going into a low pressure state that the evaporator needs. We're going into a medium pressure. And this medium pressure, what that does is it creates the flash off effect, right? So we're familiar with the fact of TXV as an example. We go through that TXV and we're roughly 80-ish% liquid coming out of it, and that other 20-ish% vapor coming out of the TXV or the metering device, right? That's very standard procedure whenever we go from a high pressure to a low pressure state. We're going to have some flash gas in the process. That flash gas reduces efficiency. It reduces our enthalpy, or our ability to take in more heat. It keeps a higher enthalpy than what we want to have. So what we do, that liquid refrigerant doesn't change in subcooling value. Okay, this is all liquid in here. Liquid refrigerant will stay in the bottom, but our vapor, the flash gas itself, will rise to the top of this chamber. Okay, this is just a big hunk or this is a big cylinder on the side of the chiller, right, with the economizer. So you're very, very specific to calling out the economizer in that process. That is what this is right here. The big, usually it'll be fully insulated and everything else. So we have our first stage of pressure drop. We have our 80% liquid stays here in this in a medium pressure state. That medium pressure vapor rises to the top of this chamber, and there is a pipe on the top of that then feeds up into the compressor. Now, if this was a three-stage machine, not trying to confuse this, but just for clarity, if this was a three-stage, you would see two pipes up here. Being that this is only a two-stage compressor with a CVHF, which is our example, you will see just one pipe. And that's one really quick way to determine on these chillers. Do I have a three-stage compressor or a two-stage compressor? How many pipes are on the economizer? That will immediately tell you what you need to know. And just in case it helps, we're going to say CVHF, just so that we're fully on the same page. This gets confusing really quickly if we're not careful, so I want to be very cautious of that. Okay, so what happens from here? So we've got this standing liquid here in the bottom of the economizer. We've got this vapor, which I show goes back up into the impeller. Two things are happening in this process. Let's show both of them. On one hand, we are reducing the load on the compressor because this vapor gets drawn up into the second stage impeller, where we have also a medium pressure state coming in from the first stage. So these two refrigerant streams mix right here, and they enter into the final, or the second stage impeller, and then get turned into hot gas. Now, a big part of the work that our compressor has to do is compressing the refrigerant from its lower pressure state to its higher pressure state. All right, this is true for any compressor, scroll compressors. The higher your compression ratio, the more energy you're having to use to make that compression. Same thing is true here. What we've essentially done is we have began to reduce that compression ratio because we have introduced a medium pressure vapor back into it, back into the refrigerant stream part way into the cycle. The reason that reduces it is because we're not trying to go from low pressure to high pressure now with all of this vapor. Now all we have to do is get this medium pressure to high pressure. It has way less pressure rise necessary to still achieve a high pressure state. And because of that very fact, we're only going from medium to high pressure. The compressor has to put less work, less horsepower into this refrigerant than it would have had to do if all of that vapor went all the way back in through the suction as a low pressure. This is the fundamental purpose of that economizer, is we are reducing compressor load by not having the compressor cycle 100% of the charge as low pressure gas back to a high pressure. We can take some of that as medium pressure, step it up to high pressure, reduce the total work the compressor has to do in the end. Now, that's not the only thing being accomplished here. This is just one side of it. The other piece of this is in the liquid refrigerant that's left, and that's where we get into our enthalpy chart. So this is a basic saturation chart curve. All right, there's nothing fancy going on here. What I've got is condenser pressure, my CP, my medium pressure, which is my MP, and my evaporator pressure, which is EP. That's what I'm establishing here. So this is my pressure on the chart. This is the actual enthalpy. Remember, enthalpy is just is referencing heat content. So the further to the left we are on this chart, the more room we have to take in heat. And the further to the right we are, the less room we have to take in heat. That is the basic fundamental, and the higher we are on this chart, the higher the pressure we are. The lower we are, the lower the pressure. This white line shows the saturation curve the refrigerant is operating within. This is a basic enthalpy chart. When you see a saturation chart or for refrigerants, you see these curves. This is what it's showing you. It's showing you the enthalpy cycle of that refrigerant, or the saturation cycle. Now, let me explain what's happening here so that we get a concept of where we are. Our liquid refrigerant, as we come in, so let's start with point number 1. Okay, I think that will be easier to follow. So on point number 1, we are right here in the evaporator. All right, so we've gotten into the evaporator. We're actually here at the suction line, and we're returning back to the compressor. So this is point number 1. So as we go from point 1 and we've entered the suction of the compressor, and up right here we are at the compressor discharge. All right, so we have raised that compressor, or that refrigerant pressure, and we have raised its saturation. From here, we have now gone through the compressor, and we're back over here. So this was our point 1. Over here would be our point 2. Then we send that refrigerant into the condenser to point 3. So this process is when we're right here, this line, this is processing through the condenser. So we're not lowering pressure, but we're removing heat from the refrigerant. So right here, from 1 to 2, this 2 is slightly over from 1 because this is the heat the compressor put into the refrigerant. All right, so this is heat of compression. All right, that's why it's not perfectly above it. But when we go into the condenser, we're not lowering pressure in the condenser. We're just removing heat. So from 2 to 3, this is where we're processing through the condenser. So this would be point number 2. We go through the condenser, we're at point number 3. That is when we're going from a liquid or a hot gas into a liquid, hot gas into a liquid right here. So we're at the liquid side of this curve. This is our gas side, this is our liquid side. Everything in between is an intermediate state. We're between a vapor and liquid. All right. So number 3, we're leaving the condenser and we hit that first flash plate going into the economizer, and we have a split right here. This split is where the economizer's job is done. So from 4 to 5, 5 is the liquid that's left in the bottom of the economizer. From 4 to 7 is the vapor that gets sent back to the compressor and adds to that heat that you see at point 2. So this is our economizer line getting sent back to the compressor. Okay? This is where it gets blended. If you notice, even though if we had like several degrees of subcooling, let's say 10 degrees of subcooling, like some machines run, we would be over here. The fact is, though, we're not. We're right here on that saturation curve line, which means that we're maintaining a fully liquid state, but we're right at that fully liquid point, right? So we're not going into heavy subcooling like some machines like to run at. So that's what you're seeing here. The economizer, by removing that flash gas has removed all of this heat right here between 4 and 5. That heat that was here goes right here with that flash gas. And that is part of what this flash gas here is doing. It is carrying that heat away so that we have a lower enthalpy. And that's what this chart is showing you, is our enthalpy reduced. Our pressure didn't. Our enthalpy did. So now this liquid refrigerant can now handle a lot more heat to be put into it than it could have handled if we didn't send it through the economizer. Because if we would have gone straight from high pressure liquid to low pressure on the evaporator, you'll see how much further over to the right we are in our heat curve. So by doing this, we dramatically improve how much heat the liquid refrigerant can take in. So from 5 to 6, this is the next flash plate we go into, which is right over here. So these machines actually have a dual plate coming into the evaporator. It's about how the machine manages different load states and low load versus high load and maintaining efficiency, yada yada. Point is, there's 2 here. So you'll go through both of these plates, and then once we go medium pressure liquid to a low pressure liquid on the other side of those plates. And these 2 plates finish that pressure reduction process to get us to a low pressure saturation so that we can take in heat. Because remember, our saturation is there just for taking in heat and rejecting heat. That's the whole point of why we have the saturation we do. We need it below our water temperature to take in heat. We need it higher than our water temperature to let go of the heat. That's our very fundamental refrigeration process. It's the same thing as what we'd have with air. We're just doing it with water in this case instead of air. So as we come through this line, we are now into this 6 to 1 stage, which this is our superheating stage. So we're going from a saturated liquid refrigerant, low pressure, or at evaporator pressure, and we're flowing up to our point 1, which we're back to our suction line coming into the compressor once we hit this point. And the whole cycle starts over again. So this is the second part of what the economizer is doing inside of a Trane compressor, or in a Trane CVH refrigerant circuit. Reduces compressor load by recycling some of that medium pressure vapor, but also improves our enthalpy going into the evaporator, giving us better heat content. These two things together make a very effective machine. So that is the basic process of a Trane water-cooled centrifugal with the economizer. It is a lot. If it's not something you're familiar with, it's okay. This is where just taking time to read more material on it, get more familiar with it. This is something I go through multiple times and in detail inside of my certification course at chilleracademy.com. So if that's something you're interested in doing, I would encourage you to go there. We can discuss things further. There's a lot of other questions people have had around these same topics. You can read through their questions in the lesson comments. All that information is there if you need it any further. But just from it all bundled up in one high-level perspective, that is how that machine is functioning and why the economizer exists. The economizer does get slightly more complicated because it adds another layer of pressure drop inside of the economizer. We don't need to do that today. That's just kind of taking it to another level. That's what you'll see with a 3-stage machine versus 2-stage. Right? The 2-stage is the simplest version of this. We're just going to stick to that for now.